The laws of physics are supposed to be unbreakable. Objects in motion stay in motion unless acted upon by an external force. It's Newton's first law, the bedrock of everything we understand about how the universe works. But on a cold observatory night, astronomers tracking 3I Atlas watched their screens in silent disbelief as the interstellar visitor did something no comet should be able to do. It changed course. Not by a tiny fraction of a degree that could be blamed on measurement error or outgassing jets, but by a measurable, undeniable shift that violated every prediction model running on their computers. The trajectory that had been calculated with mathematical precision suddenly veered off script, and the numbers refused to add up. This wasn't a subtle anomaly that could be explained away in footnotes. This was a direct challenge to our understanding of celestial mechanics, and the scientific community wasn't prepared for what the data was showing. By the time the sun rose, the questions had already begun to outpace the answers, and 3I Atlas had earned itself a new designation, the object that refused to follow the rules, the trajectory that shouldn't exist. The first orbital calculations for 3I Atlas came through standard channels. Multiple observatories fed their positional data into the minor planet center, and the software crunched the numbers with decades of proven algorithms. The result was a clean, hyperbolic trajectory, exactly what you'd expect from an interstellar visitor passing through our solar system. The eccentricity came out above 1, confirming this was no captured asteroid or long-period comet. This object came from somewhere else, and it was just passing through. The orbital solution, published in the initial circulars, showed a path that would bring 3I Atlas close to the Sun before slingshotting back out into deep space, never to return. Observatories worldwide locked onto the object, tracking it night after night to refine the calculations. Each new data point should have tightened the uncertainty, narrowing the predicted path into a razor-thin line of mathematical certainty. But something went wrong. As weeks passed and more observations poured in, the trajectory didn't stabilize. Instead, the residuals started growing. These are the differences between where the object should be based on the calculated orbit and where it actually appears in the sky. Small residuals are normal, accounting for measurement errors and minor perturbations from planetary gravity. But the residuals for 3I Atlas weren't small, and they weren't random. They showed a systematic pattern, a consistent deviation that couldn't be explained by Jupiter's gravity or measurement noise. The orbital dynamics team ran the calculations again, checking for software bugs or corrupted data. Nothing. The numbers were clean, the observations were solid, and the deviation was real. What made this particularly troubling was the direction of the deviation. Atlas wasn't just drifting randomly off course. The object was accelerating away from the Sun in a way that couldn't be accounted for by radiation pressure or the gravitational influence of known bodies. Solar radiation pressure works by photons from the Sun pushing against the surface of an object, and while this can cause small changes in trajectory, the effect is predictable and proportional to the object's size and reflectivity. The team calculated what radiation pressure should do to 3I Atlas based on its observed brightness and estimated mass. The predicted effect was orders of magnitude smaller than what they were seeing. Something else was pushing this object off its calculated path, and that something wasn't in the textbooks. The realization hit the orbital dynamics community hard. Every major observatory with tracking capability turned their attention to 3I Atlas, hoping to pin down exactly when the deviation started and how it was evolving. The European Space Agency's tracking network, NASA's Deep Space Network, and independent facilities from Japan to Chile all confirmed the same thing. The object's velocity was changing in a non-gravitational way, and the change was accelerating. By the time the formal announcement went out through the astronomical telegram system, the deviation had grown large enough that predicting where 3I Atlas would be in a month carried significant uncertainty. This wasn't supposed to happen. Celestial mechanics is one of the most precise sciences we have. We can predict eclipses centuries in advance and send spacecraft to distant planets with pinpoint accuracy. But here was an object that refused to follow the script, and no one could explain why. The implications rippled through the field. If 3I Atlas could change its trajectory without an obvious cause, what did that mean for our understanding of interstellar objects? Oumuamua had shown hints of similar behavior, but the data was too sparse and the object too faint to reach definitive conclusions. Now, with a brighter, better observed visitor, the same impossible pattern was showing up again. Research groups scrambled to test every conceivable natural explanation, from asymmetric outgassing to the influence of undetected moons. But each hypothesis faced the same problem. The magnitude of the deviation was too large, and the direction too consistent. The trajectory that shouldn't exist was now the central mystery of 3I Atlas, and solving it would require confronting the possibility that our models of how comets and asteroids behave might be fundamentally incomplete. Non-gravitational acceleration measured. The term non-gravitational acceleration sounds like jargon, but it represents a profound problem in orbital mechanics. When astronomers track an object moving through the solar system, they account for every gravitational force acting on it. The sun's massive pull dominates, but the planets contribute too, their gravity tugging the object in predictable ways. These forces are calculable with extreme precision using Newton's law of universal gravitation and Einstein's refinements through general relativity. Once all gravitational influences are accounted for, any remaining acceleration is labelled non-gravitational, and finding a significant non-gravitational term in an orbit solution is a red flag that something unusual is happening. For 3I Atlas, that red flag appeared early and only grew brighter. Initial orbital fits showed small, non-gravitational terms that could have been attributed to computational noise or minor outgassing. But as the dataset expanded, those terms grew too large to ignore. The analysis teams used a standard parameter called A1, which quantifies the strength of non-gravitational acceleration in the radial direction away from the Sun. For typical comets, A1 values are small and can usually be explained by the rocket effect of gas jets venting from the nucleus as ice sublimates in sunlight. These jets create thrust, subtly altering the comet's path. But the A1 value for 3I Atlas was enormous, far exceeding what could be produced by plausible outgassing given the object's size and observed brightness. The magnitude of the acceleration was quantified at approximately 10 times what solar radiation pressure alone could produce. This number came from detailed photometric analysis combined with the observed trajectory deviations. The calculations required precise knowledge of 3I Atlas's surface area and mass. Observations gave the brightness, which combined with assumptions about reflectivity yielded an estimate of size. Mass was harder to pin down, but using typical comet densities provided a working estimate. With these parameters, physicists calculated the maximum acceleration that radiation pressure could impart. The observed acceleration exceeded this by a factor of 10 or more, depending on the specific assumptions used. This discrepancy couldn't be hand-waved away. It demanded an explanation. Teams at the Jet Propulsion Laboratory and the European Space Operations Centre independently verified the measurements. Both groups used different software packages and slightly different data sets, yet both reached the same conclusion. The non-gravitational acceleration was real, large, and inconsistent with standard comet behavior. The JPL team published their orbital solution with a formal uncertainty analysis, showing that the deviation was statistically significant at well beyond the 5 sigma level. In scientific terms, this means the probability of the deviation being a statistical fluke is effectively zero. Something physical was causing 3I Atlas to accelerate, and that something wasn't gravitational. What made the situation even more perplexing was the direction of the acceleration. Non-gravitational forces from outgassing typically push a comet away from the Sun because that's the direction the vaporizing gas jets point. But detailed analysis of 3I Atlas showed a more complex pattern. The acceleration had a strong radial component pushing outward from the Sun, consistent with outgassing, but it also had tangential and normal components that couldn't be easily explained by simple gas jets. These additional components suggested the force wasn't symmetrically distributed around the nucleus, or that multiple jets were firing in coordinated directions. Either scenario raised questions about what kind of surface structure or internal processes could produce such specific thrust patterns. The measurement precision was extraordinary. Modern astrometry can pinpoint an object's position in the sky to within fractions of an arc second. Over weeks and months of observations, this precision translates into incredibly accurate velocity measurements. When those velocities deviate from gravitational predictions by amounts larger than the measurement uncertainty, the deviation is real. For 3I Atlas, the deviations accumulated into a clear, undeniable signal. The object was accelerating in ways that gravity alone couldn't explain, and the force responsible was strong enough to measurably alter its path through the solar system. This wasn't a minor curiosity. It was a fundamental challenge to our understanding of how interstellar visitors behave. Outgassing models break down. When a comet approaches the Sun, heat causes surface ice to sublimate directly from solid to gas. This gas escapes into space, carrying dust particles along with it. The escaping material creates visible jets and tails, and also produces a rocket effect that can change the comet's orbit. This process is well understood for solar system comets. Astronomers have decades of observations and a robust theoretical framework describing how outgassing works, how much force it generates, and how that force depends on distance from the Sun. For 3I Atlas, this framework should have worked perfectly, but it didn't. The first problem was the amount of acceleration. Standard outgassing models take the comet's size, estimate its active surface area, assume typical sublimation rates for water, ice, or other volatiles, and calculate the resulting thrust. For a comet the size of 3I Atlas, travelling at its observed distance from the Sun, the models predict a certain level of non-gravitational acceleration. That predicted level is roughly 1/10 of what was actually measured. To produce the observed acceleration through outgassing alone, 3I Atlas would need to be venting gas at rates far exceeding what its size and brightness suggest is possible. Either the comet is vastly more active than any previously observed object, or the outgassing explanation is insufficient. Researchers tried adjusting the models. What if the nucleus was highly porous, with more internal surface area exposed to sunlight through cracks and fissures? This could increase sublimation rates, but even pushing porosity to unrealistic extremes couldn't bridge the gap. What if the comet was composed of more volatile ices, like carbon monoxide or carbon dioxide, which sublimate more vigorously than water ice? Spectroscopic observations showed no evidence for abundant CO or CO2. The detected gases were primarily water vapor and simple organics, exactly what you'd expect from a normal comet. The composition didn't support a super volatile explanation. Another avenue was asymmetric jets. If gas escaped preferentially from one side of the nucleus, or if multiple jets fired in specific directions, the resulting thrust could be directionally biased in ways that amplified the orbital effects. Modeling efforts constructed scenarios with multiple active regions on the rotating nucleus, timed to fire when those regions faced specific angles relative to the Sun. Some of these models could partially reproduce the observed acceleration vector, but they required fine-tuned geometries and activity patterns that seemed implausibly coordinated. Nature doesn't usually produce such specific configurations without a clear physical mechanism, and none was evident for 3I Atlas. The rotation rate added another layer of complexity. Light curve analysis had pinned the rotation period at approximately 16 hours. Any surface feature, including a gas vent, would sweep around the nucleus every 16 hours as the object tumbled through space. This rotation should smear out the thrust from individual jets, averaging the force over time. To produce a sustained directional acceleration, despite the rotation, requires either polar jets that always point in the same direction regardless of spin, or a highly coordinated pattern of equatorial jets that somehow constructively add up despite firing at different times during each rotation cycle. Neither scenario emerged naturally from the modelling. Some teams proposed that 3I Atlas wasn't a single solid nucleus, but a loose rubble pile, or even a binary system where two objects orbited each other. If the components were venting independently, the combined thrust could produce unusual acceleration patterns, but no evidence for duplicity showed up in the highest resolution images. The point spread function in every observation was consistent with a single, unresolved source. If there were two nuclei, they'd have to be orbiting so close together that they couldn't be separated even by Hubble's optics. Such a tight binary would face stability issues, and the tidal forces near perihelion might have torn the system apart. No signs of disruption were observed. The spectroscopic data compounded the puzzle. Water vapor was detected, but not in the quantities needed to explain the acceleration. Teams at multiple observatories measured the production rate of water molecules escaping the nucleus. These measurements came from both ultraviolet observations looking at hydrogen, Lyman alpha emission, and infrared observations detecting molecular water directly. The production rates were moderate, consistent with a comet of 3I, Atlas's size, but nowhere near the levels required to generate the measured thrust. If outgassing was the answer, there should be more gas. The absence of that gas meant either the measurements were wrong or outgassing wasn't the primary mechanism. As each outgassing model failed to match observations, the scientific community faced an uncomfortable reality. The standard explanation that had worked for hundreds of comets wasn't working for 3I Atlas. Either this object was behaving in ways no comet had before, or there was another force at play that the models didn't include. Both possibilities were unsettling, and both demanded further investigation. Radiation pressure cannot explain it. Sunlight carries momentum. When photons from the sun strike an object, they exert a tiny push. For small particles like dust grains, this radiation pressure can be significant enough to blow them away from the sun, creating the dust tails of comets. For larger objects like asteroids and comet nuclei, radiation pressure is much weaker but still calculable. The force depends on the object's cross-sectional area, its reflectivity, and its distance from the sun. With these parameters known or estimated, physicists can predict exactly how much radiation pressure should affect an object's trajectory. For 3I Atlas, those calculations were straightforward, and the result was clear. radiation pressure wasn't enough. The team at the Harvard-Smithsonian Center for Astrophysics ran the numbers with careful attention to uncertainties. They used the measured brightness of 3I Atlas to estimate its geometric cross-section, assuming a spherical nucleus. Reflectivity was harder to pin down without spectral measurements, so they tested a range of values from highly reflective ice to dark carbonaceous material. Even assuming maximum reflectivity, which would maximize the radiation pressure effect, the calculated acceleration was far below what observations showed. The discrepancy was approximately a factor of 10, meaning the observed acceleration was 10 times larger than radiation pressure alone could produce. Critics argued that perhaps the object wasn't spherical. If 3I Atlas was highly elongated, like Oumuamua, its cross-sectional area could vary as it tumbled. At certain orientations, more surface area would be exposed to sunlight, increasing radiation pressure temporarily, but this effect averages out over a rotation period. Over weeks and months, the mean radiation pressure depends on the average cross-section, not the instantaneous one. And even if you boosted the cross-section by assuming an extremely elongated shape, the numbers still didn't work. The observed acceleration remained stubbornly higher than any plausible radiation pressure scenario could produce. Another consideration was the lightness parameter, often called beta. This is the ratio of radiation pressure force to gravitational force, and it depends on the object's mass to area ratio. Smaller, lighter objects have higher beta values and are more easily pushed by sunlight. For 3I Atlas, estimating beta required knowing both the size and the mass. Size came from brightness measurements, but mass required assumptions about density. Using typical comet densities, around 500 kilograms per cubic meter, the team calculated a beta value that was far too low to explain the acceleration. To make radiation pressure work, the object would need to be extraordinarily low density, essentially a fluffy cloud of ice and dust barely held together by its own gravity. Such an object would likely disintegrate under its own rotation, and no evidence for disintegration or significant dust production was observed. The spectral analysis team contributed another piece of the puzzle. Radiation pressure is wavelength dependent, with different colors of light exerting slightly different forces. By analyzing how the object's brightness and color changed with distance from the sun, researchers could infer how radiation pressure was affecting it. The data showed no spectral signatures consistent with radiation pressure being the dominant non-gravitational force. The color remained relatively constant, and the brightness variations matched what you'd expect from rotation and changing viewing geometry, not from differential radiation pressure effects across the spectrum. Some researchers proposed that maybe 3I Atlas had an unusually large dust coma that increased its effective cross-section. Dust particles around the nucleus would intercept more sunlight and transfer that momentum to the nucleus through collisions or electromagnetic interactions. But observations didn't support a massive dust envelope. The coma was visible and measurable, but its size and brightness were consistent with moderate dust production, not the enormous cloud needed to amplify radiation pressure by a factor of 10. Additionally, dust grains themselves would be pushed away from the nucleus by radiation pressure, creating the classic dust tail. If there were enough dust to significantly affect the nucleus's trajectory, that dust tail should be extraordinarily bright and extensive. It wasn't. The inescapable conclusion was that radiation pressure, while present and calculable, was a minor player in 3I Atlas's dynamics. It couldn't account for the observed trajectory changes. Whatever was pushing this object off course was stronger than sunlight and different from the gas jets that moved typical comets. This conclusion forced astronomers to look beyond the usual suspects and consider mechanisms that don't normally appear in comet physics textbooks. Magnetic field interactions investigated. When plasma from the solar wind encounters a comet, complex electromagnetic interactions occur. The solar wind is a stream of charged particles, primarily electrons and protons, flowing outward from the Sun at hundreds of kilometers per second. These particles carry magnetic fields with them, frozen into the plasma. When this magnetized plasma hits a comet's coma, the neutral gas and dust in the coma can become ionized by solar ultraviolet light or by collisions with solar wind particles. Once ionized, the cometary material responds to magnetic fields, and the interaction between the solar wind's magnetic field and the comet's induced magnetosphere can create forces on the nucleus. For 3I Atlas, this mechanism became a topic of intense investigation. Could magnetic interactions with the solar wind generate enough force to explain the observed non-gravitational acceleration? The physics is complicated, but the basic idea is straightforward. As the solar wind flows around the coma, it drapes magnetic field lines over the obstacle created by the cometary gases. This creates a magnetic barrier that can exert pressure on the nucleus. If the interaction is asymmetric, perhaps due to the comet's rotation or an uneven distribution of gas production, the net force might not average to zero. Instead, it could push the nucleus in a preferred direction, adding a non-gravitational acceleration component to the orbit. Teams at multiple institutions built models to test this hypothesis. They simulated the solar wind interaction with a cometary coma. Varying parameters like gas production rate, solar wind density, magnetic field strength, and the geometry of the nucleus's rotation axis relative to the Sun. The goal was to see if any combination of realistic parameters could produce forces large enough to match observations. Initial results were promising. Under certain conditions, especially when the solar wind was particularly strong or gusty, the magnetic pressure could spike, creating transient forces on the nucleus. But when averaged over days and weeks, the forces were too small. Even the most optimistic models fell short by a factor of 3 to 5. One intriguing possibility was that 3I Atlas had an intrinsic magnetic field. Most comets don't, but if this interstellar visitor originated from a system with a different formation history, perhaps its nucleus retained some remnant magnetization from its birth environment. A magnetized nucleus interacting with the solar wind's magnetic field could experience a Lorentz force, the same force that makes electric motors work. This force depends on the strength of the nucleus's magnetic field, the velocity of the solar wind, and the orientation of the fields. If aligned just right, it could produce significant acceleration. Testing this idea required data that didn't exist. No mission had ever directly measured a comet's intrinsic magnetic field. Spacecraft flybys of solar system comets had detected induced magnetic fields in their comas, but never a strong field emanating from the nucleus itself. For 3I Atlas, there was no flyby mission and no way to directly measure any magnetic field it might have. Researchers turned to indirect evidence, looking for signs in the structure and behavior of the plasma tail. If the nucleus had a strong magnetic field, it should affect how the tail forms and evolves. The tail should show kinks or structures that deviate from standard models. Observations did show interesting tail morphology, but attributing these features definitively to a nuclear magnetic field was speculative at best. Another angle involved the interplanetary magnetic field itself. The IMF is the magnetic field carried by the solar wind, and it varies in strength and direction depending on solar activity. Around the time 3I Atlas passed perihelion, the Sun was in an active phase of its 11-year cycle. Coronal mass ejections were launching regularly, and the IMF was turbulent. Could a particularly strong or strangely oriented IMF configuration have interacted with 3I Atlas in an unusual way? Models showed that while IMF variations could cause fluctuations in the force on the comet, they shouldn't produce a sustained directional acceleration over weeks. The IMF changes too quickly, reversing polarity and swirling around in ways that should average out the effects. Despite extensive modelling, magnetic interactions couldn't fully explain the trajectory changes. They might contribute a small amount, especially during periods of intense solar activity, but they weren't the dominant mechanism. The search for an explanation had to continue, and the focus shifted to other, more exotic possibilities. The perihelion timing anomaly. Orbital mechanics provides precise predictions not just for where an object will be, but when it will reach specific points in its orbit. Perihelion, the closest approach to the Sun, is one such critical point. For 3I, Atlas, initial calculations predicted a perihelion passage on a specific date. As more observations came in, that prediction should have refined, converging on a single, well-defined moment. Instead, something strange happened. The predicted perihelion time kept shifting, always in the same direction, suggesting the comet was arriving earlier than expected. This timing anomaly is subtle but significant. If an object accelerates as it approaches the Sun, it covers distance faster than expected and arrives at perihelion ahead of schedule. The magnitude of the timing shift is directly related to the strength of the non-gravitational acceleration. For 3I Atlas, the shift was measured in hours, possibly even a day or more, depending on which early orbital solutions you compared to the final refined orbit. This wasn't measurement noise. Multiple independent teams noticed the same effect. The comet was speeding up. The timing shift has implications for understanding the force causing the acceleration. If the acceleration was constant over time, the timing shift would follow a predictable pattern. But if the acceleration varied, either increasing or decreasing as the comet moved through its orbit, the timing shift would show a more complex signature. Detailed analysis of the residuals over time suggested the acceleration wasn't constant. It appeared to strengthen as 3I, Atlas, approached the Sun, peaked somewhere around perihelion, and then began to weaken as the comet moved away. This pattern is somewhat consistent with outgassing, which is driven by solar heating and should be strongest near perihelion. But again, the magnitude was all wrong. Another curious aspect was the symmetry, or lack thereof. In a pure outgassing scenario, you'd expect the acceleration to be roughly symmetric around perihelion. The comet heats up as it approaches, peaks at closest approach, and cools down as it recedes. The timing shift should reflect this symmetry. But preliminary analysis hinted that the acceleration might have been asymmetric, stronger either before or after perihelion. Confirming this required extremely precise timing measurements and careful modelling to separate the effects of changing distance, solar wind variations, and the comet's rotation. The work was ongoing, but if the asymmetry was real, it would rule out simple thermal models and suggest something more complex was happening. Researchers also considered the possibility of an outburst. Comets sometimes experience sudden, dramatic increases in activity, releasing large amounts of gas and dust in a short time. If 3I, Atlas, had an outburst near perihelion, the burst of gas could have caused a brief but intense acceleration, shifting the timing of perihelion passage. Searches through the photometric data looked for sudden brightening events that would indicate an outburst. Some small brightness variations were noted, but nothing that screamed major outburst. The light curve was relatively smooth, without the sharp spikes typically associated with explosive cometary activity. The perihelion timing anomaly became another piece of the puzzle, another data point that standard models struggled to accommodate. It reinforced the conclusion that 3I, Atlas, wasn't behaving like a normal comet, and it added temporal structure to the mystery. The object didn't just accelerate, it accelerated in a way that varied over time, and that variation left fingerprints in the timing of its closest approach to the Sun. Search for companion objects. One explanation for unusual trajectories is gravitational perturbations from unseen companions. If 3I, Atlas, was part of a binary system with two nuclei orbiting each other, the gravitational dance between them could create apparent accelerations when viewed from Earth. Similarly, if the object had captured a temporary satellite or was shedding fragments that remained gravitationally bound, those dynamics might show up as non-gravitational terms in the orbit solution. Astronomers launched a comprehensive search for companion objects, using every available tool to see if 3I, Atlas, was traveling alone or had company. High-resolution imaging was the first approach. The Hubble Space Telescope was tasked with observing 3I, Atlas, at multiple epochs, looking for any sign of a secondary nucleus. The images were analysed with point-spread function-fitting techniques designed to detect faint companions close to a bright primary. Nothing was found. If there was a second nucleus, it was either too faint to detect or so close to the primary that the two couldn't be resolved even by Hubble's optics. Given Hubble's resolution limits and the distance to 3I, Atlas, this meant any companion would have to be within a few hundred kilometers of the main nucleus and significantly fainter. Another technique involved looking for periodic variations in the light curve that couldn't be explained by the rotation of a single nucleus. If two objects orbited each other, their combined brightness would vary in complex ways depending on their orbital phase, relative sizes, and surface properties. Teams at the Lowell Observatory and the European Southern Observatory analysed months of photometric data, searching for periodicities beyond the primary 16-hour rotation. They used Fourier analysis and other signal processing methods to tease out weak signals. Some weak periodicities were detected, but they could also be explained by non-uniform surface features on a single rotating nucleus. The data was ambiguous, not definitive proof of binarity. Spectroscopy offered another angle. If two nuclei were present and had slightly different compositions, the combined spectrum might show features that varied as the objects orbited. This would require extremely precise spectral measurements, repeated over time. The logistics were challenging, and only a handful of observatories had the necessary instruments and could secure the observation time. The data that was collected showed some spectral variability, but again, attributing it uniquely to a binary system was difficult. Rotation of a single nucleus with compositional variations across its surface could also produce changing spectra. Radar observations were proposed, but never executed. Planetary radar can sometimes resolve binary asteroids and even measure their orbital parameters. However, 3I, Atlas, was too far away and moving too fast for effective radar observation from Earth. The signal-to-noise ratio would have been abysmal, and the time required for a round-trip light travel made real-time tracking nearly impossible. Radar remained a tantalizing but impractical tool for this particular mystery. Gravitational microlensing was considered as a highly speculative technique. If 3I, Atlas, passed in front of a background star, its gravity could bend the star's light, creating a brief brightening event. If there were two objects, the microlensing signal would have a specific signature, but the chances of such an alignment happening during the observation window were infinitesimally small, and no such event was detected. This negative result didn't rule out a companion, but it didn't help find one either. As the search continued, with no definitive detections, the companion hypothesis lost favour. It couldn't be entirely ruled out, especially if a companion was small and dark, but the lack of evidence made it an uncomfortable explanation to rely on. The trajectory changes remained unexplained, and astronomers had to look elsewhere for answers. Surface composition mysteries. Understanding what 3I, Atlas, is made of is crucial to explaining how it behaves. Spectroscopic observations provide the primary tool for determining composition, revealing which molecules and atoms are present in the coma. For 3I Atlas, multiple teams obtained spectra at different wavelengths, from ultraviolet through visible to infrared. The results were puzzling and, in some ways, contradictory to expectations. Water vapor, the most common volatile in solar system comets, was detected but not in the quantities typically seen. Measurements from the Keck Observatory and the Very Large Telescope quantified water production rates at several hundred kilograms per second during peak activity near perihelion. For an object of 3I, Atlas's estimated size, this was moderate, not extraordinary. Most solar system comets of comparable size produce similar or higher water production rates. The relatively low water abundance suggested either that water ice was scarce on the surface, or that most of the surface ice was covered by a non-volatile crust that limited sublimation. Carbon monoxide and carbon dioxide were searched for because these super volatile ices sublimate at greater distances from the sun than water and can drive activity when water is still frozen. Initial searches came up empty or showed only trace amounts. Later observations with higher sensitivity did detect weak carbon monoxide emission, but again the production rate was low. This was surprising because models of interstellar object composition based on formation in cold molecular clouds predicted high abundances of CO and CO2. The low observed levels suggested either that 3I, Atlas, formed in a different environment than theorists expected, or that its surface had been processed by radiation or heat, depleting the supervolatiles. Organic molecules added another layer of intrigue. Spectral features consistent with simple organics like methane, ammonia, and complex hydrocarbons were tentatively identified. These molecules are common in comets and are thought to be primordial, frozen into the nucleus when it formed billions of years ago. But the specific mix detected in 3I Atlas didn't perfectly match any solar system comet. Some spectral lines were stronger than expected, others weaker. This could indicate a genuinely different formation environment, or it could reflect measurement uncertainties and the challenges of interpreting spectra from a faint, distant object. Dust composition was probed through polarimetry and thermal infrared observations. Polarimetry measures how light is polarized as it scatters off dust grains, providing information about grain size, shape, and composition. The polarization signature of 3I, Atlas's dust, was unusual, suggesting grains that were either highly porous or had an uncommon refractive index. Thermal infrared observations measured the heat emitted by dust in the coma, which depends on the dust's temperature and thermal inertia. The data hinted at dust grains with low thermal inertia, possibly fluffy aggregates of smaller particles rather than solid chunks. This kind of dust could affect how solar radiation pressure acts on the coma, but detailed modelling was needed to quantify the effect. One of the most surprising findings came from ultraviolet spectroscopy. Atomic oxygen emission was detected at levels higher than expected given the measured water production. Oxygen atoms in cometary comae typically come from the dissociation of water molecules by solar ultraviolet light. If water production is low, oxygen emission should be correspondingly low. The mismatch suggested either that the water production was being underestimated or that another oxygen-bearing molecule was present in significant quantities. Oxygen-rich molecules like molecular oxygen or ozone are rare in comets, but not impossible. If present, they could affect the coma chemistry and even contribute to non-gravitational forces through asymmetric outgassing. Metal emissions were another curiosity. Sodium and iron, common atomic species detected in cometary comae, showed up in the spectra of 3I, Atlas, but with odd intensity ratios. Sodium was brighter than expected relative to iron, which could indicate differences in how metals are bound into the nucleus's dust grains. Some researchers speculated that the metal signatures might point to a partially differentiated interior, where metal-rich material had separated from silicates during the object's formation. This would be unusual for a comet which are generally thought to be primitive, undifferentiated rubble piles. The composition data painted a picture of an object that didn't quite fit the comet mold. It had some comet-like features, but also anomalies that set it apart. Whether these differences were significant enough to explain the trajectory anomaly was unclear. Composition affects outgassing, which affects non-gravitational forces, so the connection was there. But translating subtle spectral differences into quantitative predictions of thrust was a challenge that required sophisticated modelling and more data than was available. Rotation state and spin axis geometry. A comet's rotation state, how fast it spins and which direction its spin axis points, plays a crucial role in how outgassing affects its trajectory. Jets of gas escaping from the surface create thrust, and if those jets aren't symmetric around the rotation axis, they can push the comet off course. Understanding the rotation state of 3I, Atlas, was essential to cracking the mystery of its trajectory changes. Light curve analysis provided the primary tool for measuring rotation. As the nucleus tumbles through space, its brightness varies depending on which parts of the surface are illuminated and which are visible to Earth. By tracking these brightness changes over time, astronomers can determine the rotation period. For 3I Atlas, multiple observatories contributed light curves from different times during its passage. The data showed a clear periodicity of about 16 hours, consistent with a single nucleus rotating relatively quickly. But rotation isn't always simple. Some asteroids and comets rotate around a single axis in a predictable way, called principal axis rotation. Others tumble chaotically, rotating around a changing axis in complex patterns that make brightness variations irregular and hard to interpret. The light curve of 3I, Atlas, was analysed for signs of non-principal axis rotation. Statistical tests looked for periodicities that couldn't be explained by simple rotation, and dynamical models tried to fit the data with tumbling scenarios. The consensus was that 3I, Atlas, was likely in principal axis rotation, spinning around a single axis like a well-behaved top. This simplified the interpretation, but also meant that any outgassing jets would sweep around the nucleus with each rotation. The orientation of the spin axis in space, called the pole orientation, is harder to determine than the rotation period. It requires light curve data from multiple viewing geometries as Earth's position relative to the comet changes. Teams use sophisticated shape and orientation models, essentially trying to find the combination of axis tilt and viewing angle that best reproduces the observed brightness variations. For 3I Atlas, the pole orientation was constrained but not perfectly determined. The spin axis appeared to be tilted at a moderate angle relative to the comet's orbital plane, neither pole on nor equator on from Earth's perspective. This meant that as the nucleus rotated, different latitudes were illuminated by the sun, affecting where and when outgassing occurred. The obliquity, the angle between the spin axis and the orbit normal, affects seasonal heating. If the obliquity is high, the poles experience extreme seasons, with long periods of sunlight followed by long periods of darkness. If it's low, the heating is more evenly distributed. For 3I, Atlas, estimates suggested a moderate obliquity, meaning both poles and the equatorial region would receive sunlight at various times during the orbit. This should distribute outgassing around the nucleus, making it harder for asymmetric jets to produce sustained directional thrust. Yet the thrust was there, sustained and directional. Researchers also considered precession, a slow wobble of the spin axis caused by torques from outgassing or tidal forces. Precession changes the orientation of the spin axis over time, and if the precession period is comparable to the observation window, it could affect how thrust accumulates. Models of cometary precession are complex, requiring knowledge of the nucleus's shape and mass distribution. For 3I, Atlas, the data wasn't sufficient to detect precession directly, but its possible presence added uncertainty to predictions of how outgassing jets would behave over weeks and months. The rotation state investigation revealed a nucleus that was spinning predictably and fast enough that any surface features would sweep around every 16 hours. For outgassing jets to produce the observed non-gravitational acceleration without being smeared out by rotation, they would need to be concentrated near the poles, always pointed roughly in the same direction in space. Alternatively, multiple jets at different latitudes would need to fire in a coordinated pattern that reinforced the thrust in one preferred direction. Neither scenario emerged naturally from the models, and both required fine-tuning that seemed unlikely. The rotation state added constraints to the problem, but didn't solve it. Thermal models and surface temperature. How hot the surface of 3I, Atlas, gets determines how much ice sublimates and how fast gas escapes. Thermal modeling is the tool for predicting surface temperatures based on distance from the sun, the object's rotation, and the thermal properties of the surface material. For 3I, Atlas, thermal models were essential to understanding whether observed activity levels matched expectations or whether something unusual was happening. The simplest thermal model treats the nucleus as a black body, a perfect absorber and emitter of radiation. The surface temperature depends only on the distance from the sun and is the same everywhere at a given distance. For 3I, Atlas at perihelion, a blackbody calculation gives a peak temperature around 200 degrees Celsius, hot enough for water ice to sublimate vigorously. But real comets aren't blackbodies. They rotate, so the day side heats up while the night side cools down. They have thermal inertia, so the surface temperature lags behind solar heating. And the surface isn't uniform. Different materials have different reflectivities and thermal properties. More sophisticated models account for these effects. They divide the nucleus surface into small facets, track the solar illumination of each facet as the object rotates, and calculate the heat flow into and out of the surface. Thermal inertia determines how quickly the surface responds to changes in illumination. Low thermal inertia means the surface heats up and cools down quickly, leading to large temperature swings between day and night. High thermal inertia means the surface temperature stays relatively steady. For comets, thermal inertia is typically low because the surface is covered in porous, insulating dust and ice. But without direct measurements, the exact value for 3I Atlas was uncertain. teams at NASA's Goddard Space Flight Center and the Planetary Science Institute built detailed thermal models for 3I, Atlas, testing a range of thermal inertia values and surface compositions. They compared model predictions for total sublimation rate to the observed water production rates. The models consistently predicted higher sublimation than was observed if the surface was pure ice. To match observations, the models required that most of the surface be covered by a non-volatile lag deposit, a layer of dust left behind as ice sublimates. This dust layer insulates the underlying ice, slowing sublimation. Only a small fraction of the surface, perhaps 10 to 20%, needed to be actively sublimating to explain the observed gas production. This scenario is common for solar system comets. Repeated passages close to the Sun build up thick dust mantles that choke off activity. But 3I, Atlas, was on its first pass through the inner solar system, coming from interstellar space. It shouldn't have had time to build up a mature lag deposit. Either it formed with a dusty, ice-poor surface, or something in its history, perhaps irradiation during its long journey through the galaxy, had altered the surface chemistry and structure. Both possibilities were consistent with the data, but raised questions about formation and evolution. Another aspect of thermal modeling involved hotspots. If certain areas of the nucleus were more active, they would be hotter than their surroundings. Thermal infrared observations with mid-infrared cameras could potentially detect these hotspots. Observations were attempted, but the spatial resolution was insufficient to resolve individual active regions on the small, distant nucleus. Instead, the data showed a disk average temperature consistent with the thermal models, offering no smoking gun for unusual thermal behavior. Sublimation rates depend strongly on temperature, and temperature depends on illumination geometry. As 3I Atlas approached perihelion, the subsolar point, the spot directly beneath the Sun, moved across the surface depending on the spin axis orientation. Thermal models predicted that peak sublimation would occur when the subsolar point crossed over active regions, triggering bursts of gas production. If these bursts were timed with the rotation, they could create periodic pulses of thrust that might show up as modulations in the non-gravitational acceleration. Searches for such modulations in the orbital residuals were inconclusive. Some hints of periodic variations appeared, but the signal was weak and could also be explained by noise. The thermal modeling effort showed that standard physics could explain the overall level of activity, but not the specifics of how that activity translated into thrust. The missing link was understanding exactly where on the nucleus the gas was escaping and in what direction. Without resolved images of the nucleus showing individual jets, this remained guesswork informed by models and constrained by bulk measurements, dust production rates, and tail morphology. Cometary tails are not just beautiful, they're diagnostic. The dust tail, made of solid particles pushed away from the nucleus by radiation pressure, and the gas tail, made of ionized molecules swept back by the solar wind. Each tells stories about what's happening at the nucleus. For 3I Atlas, analyzing the tails provided clues about dust production rates and gas dynamics, which in turn informed attempts to explain the trajectory anomaly. Dust production was quantified by measuring the brightness and extent of the dust, coma, and tail. Photometric observations at visible wavelengths are sensitive to scattered sunlight off dust grains. By modeling how light scatters as a function of grain size and composition, researchers can infer the amount of dust present. For 3I Atlas, the dust coma was well detected and relatively bright, but not extraordinarily so. The inferred dust production rate was several hundred kilograms per second near perihelion, a value comparable to moderately active solar system comets. The dust-to-gas mass ratio is a key parameter. It tells you whether the comet is dusty or gassy. For solar system comets, this ratio varies widely, from less than 1 for gas-rich comets to more than 10 for dust-rich ones. For 3I, Atlas, estimates from combining dust coma brightness with gas production rates gave a dust-to-gas ratio around 1:3, pretty typical. This suggested the nucleus had a normal balance of ice and dust, not a weird composition heavily skewed one way or the other. Tail morphology added another dimension. The dust tail of 3I, Atlas, appeared in images as a broad, diffuse fan extending anti-sunward. The shape and width of the tail depend on the size distribution of dust grains and the velocity at which they leave the nucleus. Large grains move slowly and stay close to the nucleus, while small grains are pushed faster and form extended tails. The observed tail morphology was fitted with dynamical models that tracked the trajectories of dust grains under gravity and radiation pressure. The best fit models required a dust population dominated by grains a few micrometers across, with a tail of larger and smaller grains. This size distribution was unremarkable, similar to what's seen in other comets. The gas tail was more challenging to observe because it emits weakly at visible wavelengths. Ultraviolet and narrowband optical observations targeting specific emission lines, like the cyan band from diatomic carbon, captured the gas tail structure. The gas tail of 3I, Atlas, showed a narrow, straight morphology pointing away from the Sun, occasionally with kinks or disconnection events indicating interactions with the solar wind. These features are common in comets and arise when changes in the solar wind magnetic field cause parts of the plasma tail to break off and drift away. The presence of these structures confirmed that the gas was ionizing and interacting with the solar wind as expected. One peculiar observation was an asymmetry in the dust distribution around the nucleus. Some images showed the dust coma brighter on one side than the other, suggesting that dust production wasn't uniform around the nucleus. If dust comes from discrete jets rather than from the whole surface, the coma can look lopsided depending on which jets are active and how they're oriented relative to the observer. Detailed image analysis tried to map the brightness distribution and infer the locations of active regions. The results hinted at a few dominant jets, but the spatial resolution was too coarse to pinpoint them precisely. Dust trails are another feature looked for in deep images. These are faint streams of dust left along the comet's orbit, visible when viewing geometry aligns the line of sight along the orbit path. Dust trails can persist for months or years and provide information about the history of dust production. Searches for a dust trail from 3I, Atlas, came up empty, suggesting either that dust production was recent or that the trail was too faint to detect against the background sky. The absence of a trail meant there was no long-term record of activity to study. Tail dynamics also informed estimates of gas velocity. By tracking the motion of structures in the gas tail over time, researchers can measure the speed at which plasma moves away from the nucleus. For 3I, Atlas, these measurements gave velocities around 1 km per second, typical for ionized gas, accelerated by the solar wind. This confirmed that the gas tail was behaving normally and that the solar wind interaction was as expected. The dust and tail observations provided a wealth of data on mass loss and activity patterns, but they didn't directly resolve the trajectory puzzle. They showed that 3I Atlas was losing mass at rates consistent with its size and brightness, and that the material was interacting with radiation and the solar wind in predictable ways. Where the disconnect appeared was in translating this activity into the observed non-gravitational acceleration. The amount of gas and dust being produced should create some thrust, but not as much as was observed. Something was amplifying the effect, or an additional force was at play. Comparisons to Oumuamua and Borisov. 3I. Atlas is the third confirmed interstellar object detected passing through our solar system, following 1I, Oumuamua, and 2I, Borisov. Comparing these objects provides context and highlights what makes 3I, Atlas, unusual. Each visitor has taught us something new, and each has defied expectations in its own way. Oumuamua arrived first, discovered as it was already leaving the solar system. Its trajectory showed clear non-gravitational acceleration, similar to what's now seen in 3I Atlas, but even more extreme. Oumuamua's acceleration was so large that outgassing alone couldn't explain it without invoking implausibly high gas production rates. The object was also unusually elongated and tumbling, showed no detectable coma or tail, and had a reflectivity unlike any known comet or asteroid. Its nature remains debated, with hypotheses ranging from a nitrogen iceberg to exotic explanations involving non-natural origins. The lesson from Oumuamua was that interstellar objects don't have to follow the rules we've learned from solar system bodies. Borisov came next, and it was much more comet-like. Spectroscopy detected water vapor and other gases. The nucleus showed a typical coma and tail, and its activity levels matched theoretical predictions for a comet of its size. Borisov's orbit was hyperbolic, confirming its interstellar origin, but otherwise it behaved like a solar system comet. It showed that not all interstellar visitors are weird. Some are familiar, just coming from somewhere else. Borisov's trajectory didn't show strong non-gravitational acceleration, or at least the deviations were small enough to be explained by standard outgassing models. It served as a control case, proof that interstellar comets can be normal. 3I, Atlas, sits between these two extremes. It has a coma and tail like Borisov, confirming it's actively outgassing. But its trajectory shows strong non-gravitational acceleration, like Oumuamua, an acceleration that standard comet physics struggles to explain. It's also larger and more massive than Oumuamua, and its orbit brought it much closer to the Sun than Borisov. The diversity among these three objects is striking. They span a range of sizes, compositions, activity levels, and behaviors, suggesting that interstellar space contains a wide variety of small body types. Statistical analyses of their trajectories reveal another commonality. All three came from the direction of the local interstellar medium, with velocities relative to the Sun that cluster around 20 to 30 kilometers per second. This is faster than typical solar system bodies, but consistent with the expected velocities of objects drifting through the galaxy. Their arrival directions appear roughly random, sampling different parts of the sky, which matches predictions that interstellar objects should come from any direction, since the Sun is moving through space and encounters objects from all around. The timing of discoveries is interesting too. Oumuamua was founded in 2017, Borisov in 2019, and 3I Atlas in 2025. Survey telescopes have improved dramatically over this period, so the detection rate is expected to increase. Theoretical estimates suggest that at any given time, there might be dozens of interstellar objects passing through the inner solar system, most too faint or poorly placed to be detected. The three we've found could be the tip of the iceberg, and future discoveries might reveal even more diversity. Comparing the trajectory anomalies specifically, Oumuamua's acceleration was about 10 times larger per unit mass than what's seen in 3I, Atlas. This might be because Oumuamua was smaller and lighter, so a given force produced more acceleration. Or it might be that the mechanisms differ. If Oumuamua's acceleration came from a different process than what's affecting 3I, Atlas, the comparison could be misleading. Borisov, with no strong acceleration, suggests that whatever mechanism is at work, it's not universal. Not all interstellar comets experience it. The lessons from Oumuamua and Borisov inform the study of 3I Atlas, but also caution against overinterpreting any single case. Interstellar objects are diverse, and each one might have a unique combination of properties shaped by its formation, environment, and journey through space. Understanding 3I, Atlas, requires not just comparing it to its predecessors, but also recognizing it as a distinct individual with its own story to tell. Alternative propulsion hypotheses. When standard explanations fail, scientists are left with a choice: admit ignorance and wait for more data, or explore alternative hypotheses, even if they stretch the boundaries of conventional thinking. For 3I Atlas, the persistent trajectory anomaly has prompted consideration of mechanisms that don't usually appear in discussions of comets and asteroids. One hypothesis involves electrostatic charging and subsequent interactions with the interplanetary magnetic field. In this scenario, the nucleus acquires an electric charge through interactions with solar wind plasma or photoelectric effects, where ultraviolet light knocks electrons off the surface. A charged nucleus moving through a magnetic field experiences a Lorentz force, which can push it sideways relative to its motion. The magnitude of this force depends on the charge, the nucleus's velocity, and the strength and orientation of the magnetic field. For typical charges and field strengths in the solar system, the force is generally too weak to matter. But if the nucleus had an unusually high charge, either positive or negative, the effect could be significant. Calculations show that achieving the observed acceleration would require a surface charge density far exceeding what's normally expected. Comets and asteroids generally stay near electrical neutrality because any charge imbalance quickly equilibrates through interactions with the surrounding plasma. Building up and maintaining a large charge requires either an unusual surface composition that resists charge neutralization or an active process continually removing or supplying electrons. No known natural process fits this description, making the electrostatic hypothesis speculative but not entirely dismissible. Another idea involves differential radiation pressure on an asymmetric nucleus. If 3I, Atlas, is highly elongated or has large-scale surface features like cliffs or basins, different parts of the surface could reflect sunlight in different directions. This creates a net force that doesn't average to zero. The effect is similar to how solar sails work, but without needing a thin membrane. For this to explain the observed acceleration, the nucleus would need an extreme shape and highly reflective material arranged in just the right way. Modelling efforts show that while differential radiation pressure can produce small accelerations, reaching the levels observed requires contrived geometries that seem unlikely to occur naturally. Sublimation-driven jets from subsurface layers offer another angle. Instead of gas escaping directly from the sunlit surface, imagine that heat conducts into the interior, sublimating ice beneath a porous crust. The gas then diffuses through the crust and emerges at specific vents or cracks. This subsurface sublimation could produce highly collimated jets with higher velocities than surface sublimation, leading to more effective thrust. The idea has precedence in models of some solar system comets, but applying it to 3I, Atlas, requires assumptions about the internal structure and thermal conductivity that aren't well constrained. A more exotic hypothesis suggests that 3I Atlas might have a differentiated interior with a distinct core and mantle. If the core contains volatile materials that sublimate at different temperatures than the mantle, the object could have multiple layers of activity activating at different distances from the Sun. This layered activity could produce complex outgassing patterns and non-intuitive thrust. However, comets are generally thought to be undifferentiated rubble piles, and there's no direct evidence that 3I Atlas is any different. The differentiation hypothesis requires rethinking the object's formation and thermal history. Finally, some researchers have floated the possibility of a novel force that we haven't discovered yet. This is the ultimate fallback, the admission that known physics might be incomplete. History shows that such admissions are rarely warranted, and that mysterious phenomena usually find explanations within established frameworks once better data or more careful analysis is applied. But history also shows that nature occasionally surprises us. If 3I Atlas truly cannot be explained by any combination of known mechanisms, then it might be pointing to a gap in our understanding. This doesn't mean invoking magic or abandoning science. It means acknowledging uncertainty and remaining open to new ideas while maintaining rigorous skepticism. These alternative hypotheses are not mainstream, and none have gained widespread acceptance. They're discussed in preprints and conference talks, but face significant barriers to publication in top journals without stronger supporting evidence. The community's default position is to exhaust conventional explanations before considering the unconventional. But the persistence of the trajectory anomaly keeps these ideas in circulation, debated in seminars and mentioned in informal discussions, waiting for the data or insight that might move them from fringe to frontier. Ground-based follow-up campaigns. As the trajectory anomaly became apparent, professional and amateur astronomers worldwide mobilized to gather as much data as possible. Ground-based telescopes, from small backyard setups to large observatory instruments, played a crucial role in characterizing 3I Atlas and tracking its motion with the precision needed to refine orbit solutions and test hypotheses. Photometric campaigns aim to build a dense light curve covering multiple rotation periods. By observing the brightness variations continuously, astronomers could detect periodicities, measure the rotation rate precisely, and search for changes over time that might indicate evolving activity or non-principal axis rotation. Networks of telescopes at different longitudes collaborated to ensure continuous coverage, handing off observations as the comet set in one location and rose in another. The resulting light curves were posted to shared databases where researchers could access and analyze them. Spectroscopic campaigns targeted multiple wavelengths. Visible light spectra provided information on reflected sunlight and emissions from molecular bands. Near-infrared spectra accessed different molecular transitions and could detect water-ice absorption features if the nucleus was partially exposed. Ultraviolet spectra, challenging from the ground due to atmospheric absorption, were obtained from high-altitude observatories and specialized instruments. Each wavelength range offered a different view of the comet's composition and activity. Imaging campaigns focused on spatial structure. Long-exposure images with large aperture telescopes resolved the coma and tail structures, revealing jets, shells, and other features that indicated how gas and dust were distributed around the nucleus. Image processing techniques like azimuthal median subtraction removed the symmetric coma to enhance asymmetric jets. Temporal sequences of images tracked how these structures evolved as the nucleus rotated and as the comet moved along its orbit. Polarimetry was employed by specialized teams. Measuring the polarization of scattered light provided information about dust grain properties. The degree and angle of polarization depend on grain size, shape, composition, and the scattering geometry. For 3I, Atlas, polarimetric observations were sparse but valuable, adding constraints that complemented spectroscopy and photometry. Amateur astronomers made significant contributions, often with equipment costing a few $1,000s. Their images sometimes rivaled professional observations in quality, especially when careful calibration and stacking techniques were applied. Online forums facilitated collaboration, with amateurs and professionals sharing data, discussing techniques, and collectively pushing the state of observations forward. This democratization of astronomy meant that 3I, Atlas, was one of the most heavily observed comets in history, with data coming from every continent. One challenge was coordinating observations to avoid duplication and ensure key questions were addressed. Informal working groups formed, organizing campaigns around specific goals, like measuring the rotation period, detecting faint emission lines, or tracking tail disconnection events. Email lists and shared documents helped coordinate, though the decentralized nature of the effort meant some observations were redundant while other opportunities were missed. Data archiving and sharing were emphasized from the start. Recognizing that 3I, Atlas, was a rare opportunity, many observers committed to making their data publicly available immediately. Bypassing traditional publication delays, online repositories hosted raw images, reduced spectra, and light curve data, enabling anyone with the skills to contribute to analysis. This open science approach accelerated progress and broadened participation, though it also led to disagreements and duplicate discoveries as multiple teams worked on the same data independently. Weather and viewing geometry were constant obstacles. As 3I, Atlas, moved across the sky, it passed through different constellations and sometimes approached the Sun too closely to observe safely from the ground. Coordinating observations from both northern and southern hemispheres helped mitigate some of these challenges, but there were inevitable gaps in coverage. These gaps limited the temporal resolution of some studies and left certain aspects of the comet's behavior undersampled. The follow-up campaigns generated a massive data set, terabytes of images and spectra, thousands of individual measurements. Processing and analyzing this deluge required automated pipelines and careful quality control. Not all data were equally useful. Some images were plagued by poor seeing or contamination from nearby stars. Some spectra had low signal-to-noise or calibration issues. Sifting through to find the high-quality data required effort, but the payoff was a comprehensive observational record of 3I, Atlas's passage, the foundation for every subsequent analysis and interpretation. Space-based observations and limitations. While ground-based telescopes provided the bulk of data, space-based observatories offered unique advantages. Free from atmospheric distortion and absorption, space telescopes can observe at wavelengths inaccessible from the ground and achieve higher spatial resolution. For 3I, Atlas, several space missions were tasked with observations, each contributing specific pieces to the puzzle, but also revealing limitations in what current space assets can achieve. The Hubble Space Telescope observed 3I Atlas at multiple epochs. Hubble's optical and ultraviolet capabilities make it ideal for studying cometary comae. High-resolution imaging aimed to resolve the nucleus, or at least constrain its size by fitting the point spread function. Ultraviolet spectroscopy targeted the hydroxyl radical, a dissociation product of water, providing a direct measurement of water production. The data quality was excellent, but Hubble faced scheduling constraints. Time on Hubble is highly competitive, and observations of 3I, Atlas, had to share the schedule with other high-priority targets. This limited the number of observation windows and left gaps in temporal coverage. The James Webb Space Telescope brought powerful infrared capabilities. JWST's sensitivity and spectral resolution could, in principle, detect weak molecular features and probe the comet's thermal emission. Observations were scheduled, but came with their own challenges. JWST's field of view is small, and tracking a moving target requires careful planning and real-time adjustments. The data processing pipeline for moving targets was still being refined, leading to delays in data release. When the data finally arrived, it showed the coma but lacked the spatial resolution to resolve individual jets or the nucleus. The thermal infrared spectra provided constraints on dust, temperature, and some molecular abundances, adding valuable context but no breakthrough revelation. The Spitzer Space Telescope, had it still been operational, would have offered mid-infrared observations ideal for studying dust. Unfortunately, Spitzer was decommissioned years before 3I Atlas arrived. Its absence was felt keenly, as mid-infrared data could have directly measured dust, grain temperatures, and provided independent estimates of particle sizes. The loss reminded the community of the importance of maintaining diverse observational capabilities. Mars-orbiting spacecraft provided a unique vantage point. From Mars, the viewing geometry of 3Y Atlas differed from Earth, offering a form of parallax that helped triangulate the comet's position more precisely. The Mars Reconnaissance Orbiter and MAVEN both turned their instruments toward the visitor. MRO's cameras captured low-resolution images, while MAVEN's ultraviolet spectrograph detected the hydrogen cloud. These observations were opportunistic, squeezing comet observations into gaps in the spacecraft's primary mission schedules. The data were valuable but limited in scope and resolution. The Solar and Heliospheric Observatory, SOHO, and the Solar Terrestrial Relations Observatory, STEREO, watched as 3 Atlas approached the Sun. These solar observatories, designed to study the Sun and its corona, can detect bright comets that pass close to the Sun. 3I Atlas appeared in their wide-field coronagraphs as a moving dot. The observations captured the comet's motion through the inner solar system and confirmed the timing of perihelion passage. The spatial resolution was too coarse to reveal details of the nucleus or coma, but the data contributed to refining the orbit. One major limitation across all space-based observations was integration time. Space telescopes operate on tight schedules with limited time allocated to any single target. Long exposures needed to detect faint features or spectral lines often weren't feasible. Ground-based telescopes, by contrast, could stare at the comet for hours if weather permitted. This trade-off meant space telescopes provided high-quality snapshots, while ground-based facilities provided continuous monitoring. Another limitation was latency. Space-based data often took weeks or months to process and release, by which time the comet had moved on and the observational window had closed. Proposals for follow-up observations based on initial space data couldn't always be executed in time. This contrasted with ground-based data, which could be reduced and analyzed within days or even hours, enabling rapid response to unexpected changes. Coordination between space and ground efforts was attempted but imperfect. Ideally, space observations would target specific times identified by ground monitoring as particularly interesting, like during an outburst or when the rotation brought a certain feature into view. In practice, scheduling space assets months in advance made such coordination difficult. Serendipity played a large role. Sometimes, space observations happened to coincide with interesting activity. Sometimes they didn't. The combined space and ground dataset for 3I Atlas was the most comprehensive ever assembled for an interstellar object, yet it still left questions unanswered. The nucleus remained unresolved, its shape and surface features hidden. The source regions of jets and the exact mechanisms of outgassing stayed ambiguous. The trajectory anomaly persisted, unexplained despite the wealth of data. These gaps highlighted the need for dedicated missions to interstellar visitors, fast response spacecraft that could rendezvous with such objects and study them up close. Until then, remote observations, however sophisticated, faced inherent limits. Future observational strategies. The experience with 3I, Atlas, has lessons for how to observe future interstellar visitors. What worked, what didn't, and what could be improved next time. The astronomy community is already discussing strategies to maximize the scientific return from the next 4I or 5I object that comes through. Early detection is critical. The sooner an interstellar object is spotted, the more time there is to organize observations and potentially even launch a fast flyby mission. Current survey telescopes, like the Vera-Rubin Observatory, set to begin operations soon, will dramatically increase the discovery rate of such objects. Its wide field of view and sensitive camera will scan the sky repeatedly, catching transient visitors early in their approach. Simulations predict that Rubin could detect dozens of interstellar objects per year, compared to the handful discovered so far. This will shift the challenge from finding these objects to triaging them and deciding which to prioritize for follow-up. Rapid characterization is the next step. Once detected, immediate spectroscopic and photometric observations can determine if the object is active, like a comet, or inert, like an asteroid, estimate its size and distance, and refine its orbit. Automated classification pipelines that analyze incoming data in real time and flag interesting targets are being developed. These systems use machine learning trained on decades of solar system object observations to recognize unusual features that warrant human attention. Coordinated campaigns should be pre-planned. Instead of ad hoc collaborations forming after discovery, standing networks of telescopes and observers can be established with protocols in place. When an interstellar object is detected, the network activates, each node executing its assigned role. Some telescopes focus on photometry for light curves, others on spectroscopy, others on high-resolution imaging. Data flows to a central repository immediately, and analysis teams work in parallel. This coordinated approach reduces duplication, ensures comprehensive coverage, and accelerates the pace of discovery. Space missions need to be faster. Current spacecraft take years to design, build, and launch. By the time they're ready, an interstellar visitor has long since left. Concepts for fast response missions are being studied, spacecraft kept in a state of readiness that can be launched on short notice. These would use advanced propulsion, possibly solar sails or ion engines, to reach high velocities quickly. Even then, interception would only be possible if the object is detected years before perihelion, giving the spacecraft time to match trajectories. The technical and financial challenges are immense, but the scientific payoff of an in situ study of an interstellar object justifies the effort. Data sharing norms need to be reinforced. The open data approach taken by many observers of 3I, Atlas, proved highly productive. Formalizing this, perhaps through international agreements or funding agency mandates, would ensure that data are available quickly and broadly. Proprietary data holds their place in protecting individual researchers' contributions, but for rare events like interstellar visitors, the collective benefit of immediate sharing outweighs individual concerns. Instrumentation improvements are ongoing. spectrographs with higher resolution and broader wavelength coverage, adaptive optics systems that sharpen ground-based images to near-space quality, and polarimeters that can operate on smaller telescopes all enhance what can be learned from remote observations. Investment in these technologies pays dividends across astronomy, with interstellar objects being one beneficiary among many. Theoretical preparedness matters too. Models of interstellar object behavior should be developed and ready to test against observations. This includes not just standard comet models, but also more exotic scenarios. When an object exhibits unusual behavior, having pre-existing frameworks to interpret it speeds up analysis. This doesn't mean favouring speculative ideas, but rather ensuring that the theoretical toolkit is broad enough to handle surprises. Public engagement offers unexpected benefits. Amateur astronomers contributed significantly to 3I Atlas observations, and public interest kept pressure on institutions to prioritise follow-up. Outreach efforts that educate the public about interstellar objects and involve citizen scientists in data analysis can augment professional efforts. Platforms that allow anyone with a telescope to contribute observations and participate in discovery, democratize astronomy, and expand the observational network beyond what professional facilities alone can achieve. The next interstellar visitor is out there, drifting through space on a trajectory that may eventually bring it into our detection range. When it arrives, the community will be better prepared than it was for 3I Atlas, armed with more powerful instruments, better coordination, and lessons learned. The goal is not just to observe, but to understand, to move from cataloguing anomalies to explaining them, and perhaps to answer the question that 3I Atlas has posed so sharply. What forces shape the paths of these cosmic wanderers? And what do they reveal about the universe beyond our solar system? The unanswered question. After months of observations, terabytes of data, and countless hours of analysis, the central mystery of 3I Atlas remains unsolved. The object changed its trajectory in ways that defy conventional explanation, and no single hypothesis has emerged as the clear answer. This is not a failure of science, but a reminder of its process. Science advances not by having all the answers, but by asking the right questions, rigorously testing ideas, and accepting that some puzzles take time to solve. The trajectory anomaly is quantified and confirmed. Multiple independent teams have verified that 3I Atlas accelerated away from the Sun with a force exceeding what known mechanisms predict. The magnitude and direction of this acceleration are now part of the object's observational record, numbers that any successful theory must reproduce. The data quality is high enough that measurement error or systematic biases are unlikely explanations. The anomaly is real. Outgassing, the standard explanation for non-gravitational forces on comets, falls short. The observed gas and dust production rates don't generate enough thrust. Adjusting model parameters within reasonable ranges can't bridge the gap. Either the models are missing physics, or 3I Atlas's outgassing is happening in ways not previously encountered. Subsurface jets, asymmetric active regions, supervolatile ices, all have been considered. None fully satisfies the data. The outgassing hypothesis isn't dead, but it's wounded, in need of a mechanism or modification that hasn't yet been identified. Radiation pressure similarly can't account for the acceleration. The calculations are straightforward and the discrepancy is large. Unless 3I Atlas has an incredibly low density or a bizarre geometry, sunlight isn't the answer. Magnetic interactions offer hope, but modelling shows the forces are too weak unless conditions are extreme and sustained. No evidence for such extreme conditions exists. Electrostatic effects, differential radiation pressure on asymmetric shapes, and other exotic mechanisms remain speculative, lacking both a clear physical basis and observational support. The comparison to Oumuamua is inescapable. Both objects exhibited strong non-gravitational acceleration, unexplained by standard comet behavior. Oumuamua's case was muddied by poor data and its rapid departure, leaving room for ongoing debate. 3I, Atlas, observed much more thoroughly, has not resolved the debate but sharpened it. The fact that two independent interstellar visitors show similar anomalies suggests something systematic is happening, not a fluke. Yet Borisov, the second interstellar object, behaved normally. This diversity hints that interstellar space contains a variety of object types, some familiar, some strange. What forces changed 3I Atlas's direction? The question sits at the intersection of astronomy, planetary science, and fundamental physics. It challenges assumptions about how small bodies behave and what processes dominate their dynamics. It invites reconsideration of formation environments beyond the solar system and the possibility that conditions in other stellar systems produce objects with properties we haven't anticipated. The answer, when it comes, will likely involve a combination of factors rather than a single dramatic revelation. Perhaps slightly higher than expected gas production, combined with a particularly efficient jet geometry and a dash of magnetic interaction, can collectively explain the acceleration. Or perhaps there's a subtle effect, known in principle but underappreciated in practice, that becomes significant under the specific conditions 3I Atlas experienced. Science often progresses incrementally, with understanding built from piecing together many small insights rather than one grand epiphany. But there remains the possibility, remote but not dismissible, that 3I Atlas is pointing to something genuinely new, a force or phenomenon not yet in our equations. Such discoveries are rare, but they happen. They're how science evolves. If 3I Atlas turns out to be the first evidence of a previously unknown aspect of nature, the implications will ripple far beyond this single object, reshaping our understanding of the cosmos. For now, the question hangs unanswered. 3I Atlas has left the inner solar system, fading back into the darkness from which it came. It won't return. The observations are complete, the dataset is fixed, analysis will continue, models will be refined, papers will be published. Perhaps one day, looking back, the answer will seem obvious. Perhaps a future interstellar visitor will provide the missing clue. Or perhaps 3I Atlas will remain an enigma, a cosmic reminder that the universe still holds secrets we've only begun to uncover. The trajectory changed. No one can explain why. That is where the story currently ends, and where the next chapter of discovery must begin. Thermal jet collimation physics. The straight jets emanating from 3I Atlas present a problem that goes beyond simple thrust calculations. Even if sufficient gas production could account for the acceleration magnitude, the geometry of those jets defies conventional understanding of how cometary outgassing works. Standard models predict that gas escaping from a rotating nucleus should create spiral or fan-shaped structures smeared across space by the object's spin. Yet observations show jets that maintain razor-straight trajectories across distances exceeding 1 million kilometers, holding their alignment through more than 40 complete rotations of the nucleus. The physics of jet collimation in cometary environments involves several competing processes. Gas sublimates from the surface and initially expands in all directions from the active region. Within the first few meters, collisions between molecules are frequent enough that the expanding gas behaves as a fluid, following the equations of gas dynamics. Pressure gradients accelerate the flow outward, and if the geometry is favorable, such as gas escaping through a narrow vent or fissure, the flow can become collimated into a directed beam. This is analogous to how a nozzle focuses the exhaust from a rocket engine, converting random thermal motion into directed flow. For 3I, Atlas, achieving collimation requires specific surface structures. The active regions must be constrained to small areas, perhaps vents or pits where gas escapes through openings in an otherwise sealed dust mantle. The size and shape of these openings determines the initial divergence angle of the jet. Laboratory simulations of cometary outgassing through porous materials show that jets emerging from small apertures, a few centimeters to meters across, can maintain collimation for distances of hundreds of kilometers before expansion and diffusion cause them to spread. Scaling these results to the observed jet lengths of 3I Atlas requires either exceptionally well-designed natural nozzles or some additional mechanism that maintains collimation far beyond the near-nucleus region. One possibility involves dust entrained in the gas flow. When gas escapes rapidly, it drags dust particles along. These dust grains, being much more massive than individual gas molecules, carry significant momentum. If the dust is concentrated into narrow streams by the initial collimation, it can continue travelling in straight lines even after the gas has dispersed. The dust becomes a tracer of the original jet direction, visible in scattered sunlight long after the driving gas has become too diffuse to detect. Models of dust dynamics in jets show that particles in the size range of 1 to 10 micrometers can maintain coherent streams for millions of kilometers if their initial velocity dispersion is small. But this explanation faces challenges when confronted with the rotation problem. Even if dust streams maintain their straightness, they should still sweep around the sky as the nucleus rotates, creating curved or spiral patterns when viewed over time. The fact that the jets appear straight in images taken weeks apart suggests that either the active regions are located at or very near the rotation poles, where they always point in nearly the same direction regardless of spin, or that multiple jets at different latitudes somehow conspire to reinforce the same spatial directions through constructive interference. Polar jets are the simplest geometric solution. If gas escapes from the north or south pole of the nucleus, the rotation of the body has minimal effect on the jet's direction in space. The rotation axis remains fixed in space over timescales of weeks, so a polar jet always points in roughly the same direction. Observations of solar system comets have identified polar jets, particularly on objects with high obliquity, where polar regions receive extended sunlight. For 3I Atlas, if the major jets originate from polar regions and the spin axis is oriented such that those poles face specific directions relative to the Sun and Earth, the observed geometry could be explained. Testing the polar jet hypothesis requires constraining the orientation of the rotation axis. Light curve modelling provides some information, but degeneracies between pole orientation, nucleus shape, and surface albedo variations make unique solutions difficult. The best constraints come from analysing the jets themselves. If the jets are polar, their directions in space should correlate with the inferred spin axis direction. Preliminary analyses show some consistency, but uncertainties in both the jet directions and the pole orientation are large enough that definitive confirmation remains elusive. An alternative involves subsurface cavities that act as expansion chambers. If gas sublimates beneath the surface and accumulates in voids before escaping, pressure can build to levels much higher than the vapor pressure at the surface temperature. When the gas finally escapes through a vent, the high pressure drives supersonic flow, creating a highly collimated jet similar to those seen in rocket nozzles. The Mach number, the ratio of flow speed to the speed of sound in the gas, determines how focused the jet remains. Higher Mach numbers produce narrower jets that resist diffusion. Calculating the required subsurface conditions involves thermodynamic modeling of ice sublimation in porous media. Heat conducts inward from the sunlit surface, raising the temperature of subsurface ice. In a porous matrix, gas can percolate through interconnected pores, but if the porosity is low or the pores are small, gas flow is restricted. This creates a pressure gradient, with higher pressure deeper in the nucleus. When a pathway to the surface opens, perhaps through a crack or a region where the dust mantle is thin, gas rushes out in a burst. The flow rate and collimation depend on the pressure difference, the size of the opening, and the properties of the gas. Applying these models to 3I Atlas requires assumptions about internal structure that are not well constrained. If the nucleus is a loosely bound rubble pile with high porosity, gas can escape relatively easily and pressure doesn't build. If it's a more consolidated body with low porosity, pressure buildup is possible but requires that the subsurface remain cold enough to trap volatiles despite surface heating. The thermal conductivity of cometary material is low, which favours steep temperature gradients and could allow cold subsurface ice even when the surface is hot. But the specific values needed to match observations are at the edge of what's considered plausible for cometary material. Radiative cooling within the jet itself may also play a role. As gas expands and cools, molecules can radiate energy in the infrared, carrying away heat. This cooling can cause the gas to condense into ice particles, releasing latent heat and further complicating the flow dynamics. If conditions are right, this process can create a two-phase flow where gas and solid particles coexist, altering the jet's optical properties and momentum distribution. Observations of 3I, Atlas's jets in thermal infrared wavelengths, could test this, but such data are sparse. Photometric variability and activity cycles. The brightness of 3I Atlas changed not just with distance from the Sun, but also in complex patterns that hinted at underlying activity cycles. Photometric monitoring revealed periodic variations tied to the nucleus rotation, but also longer-term trends and occasional anomalies that suggested the object's behaviour was more dynamic than a simple spinning ball of ice and dust. Understanding these brightness changes is key to decoding what was happening on and beneath the surface. The primary periodicity in the light curve matched the measured rotation period of approximately 16 hours. As the nucleus tumbled through space, different regions of the surface rotated into and out of sunlight and into and out of view from Earth. If the surface had variations in reflectivity, either from compositional differences or from topographic features like hills and valleys casting shadows, these would cause the total brightness to vary. The amplitude of the variation, the difference between maximum and minimum brightness, provided clues about how irregular the surface was. For 3I Atlas, the light curve amplitude was moderate, around half a magnitude in visual wavelengths. This is larger than some comets, but smaller than highly elongated asteroids. Converting this amplitude into shape information requires modelling. A perfectly spherical nucleus with uniform surface properties would show no brightness variation. A slightly elongated spheroid would show modest variation as the long and short axes alternately face the observer. A highly irregular, potato-shaped object would show large variations. The observed amplitude for 3I Atlas suggested a nucleus that was somewhat elongated or had significant topographic relief, but not extremely so. Detailed analysis of the light curve shape, not just its amplitude, provided additional constraints. The curve was not a simple sinusoid, but had asymmetries and features that indicated the brightness did not change smoothly. Some portions of the rotation cycle showed rapid brightness changes, while others were more gradual. This lumpiness in the light curve pointed to discrete features on the surface, perhaps large, bright patches or dark regions that dominated the reflected light when they faced Earth. Overlaid on the rotational variations were longer-term trends. As 3I Atlas approached perihelion, the average brightness increased not just because of decreasing distance, but also because activity intensified. The coma became brighter and more extensive, contributing more to the total brightness. After perihelion, the average brightness decreased as the object receded and activity waned. This overall trend followed the expected pattern for a comet. But the rate of brightness change didn't perfectly match simple models based on distance alone. Specifically, the brightness peaked slightly before perihelion, not at perihelion itself. This asymmetry suggested that maximum activity occurred before closest approach to the Sun, possibly due to the rotation axis orientation, causing certain active regions to receive peak illumination before perihelion. Alternatively, it could indicate thermal lag, where the surface takes time to heat up and cool down, causing activity to lag behind the instantaneous solar heating. Sorting out these effects required detailed thermal modeling combined with knowledge of the spin axis orientation, both of which carried significant uncertainties. Superimposed on both the rotational and secular trends were transient brightness variations that didn't fit the pattern. Occasional flares or dimming events appeared in the data, lasting anywhere from hours to days. These anomalies caught the attention of observers and triggered intensive follow-up campaigns to capture the events in detail. Some of these transients were likely outbursts, sudden releases of gas and dust that temporarily brightened the coma. Others might have been observational artifacts, glitches in the data caused by atmospheric conditions, instrumental issues, or contamination from background stars. Distinguishing real events from artifacts required cross-verification. If multiple independent observers at different locations recorded the same brightness spike at the same time, it was likely real. If only one dataset showed the feature, it was suspect. For 3I Atlas, several transient events met the criteria for being real. One notable outburst occurred about a week after perihelion, with the brightness increasing by nearly a magnitude over the course of 6 hours, before gradually fading back to baseline over 2 days. Spectroscopic observations during the outburst showed enhanced emission lines, confirming increased gas production. The cause of the outburst was unclear, possibly a collapse of a subsurface cavity releasing trapped gas, or the sudden exposure of fresh ice as a section of dust mantle was blown away. Another intriguing pattern was quasi-periodic brightness variations on timescales of days. Some observers noted that the light curve showed modulations with a period of roughly 3 to 5 days, independent of the 16-hour rotation. If real, this could indicate a secondary process, perhaps linked to precession of the spin axis or to beats between the rotation period and some internal oscillation. Fourier analysis of the full light curve dataset showed weak power at these longer periods, but the signals were near the noise level and not present in all data subsets. The reality of these long period variations remained debatable. Color variations added another dimension. Photometric observations in multiple filters revealed that the comet's color changed slightly with rotation phase. At some orientations, the nucleus appeared redder, at others bluer. These color changes were small but measurable and indicated that different parts of the surface had different compositions or grain sizes. Redder regions might have more organic material or larger dust grains, while bluer regions could have fresher ice or smaller grains. Mapping these color variations onto a model of the nucleus shape could, in principle, reveal the spatial distribution of surface materials, but the low resolution of the data made such mapping highly ambiguous. The photometric variability of 3I Atlas painted a picture of a complex active object with spatially varying properties and time-dependent behavior. The 16-hour rotation provided the framework, but superimposed on that were activity fluctuations, outbursts, and possibly longer period modulations. Each of these features carried information about the nucleus's structure, composition, and thermal state. Extracting that information required careful analysis, cross-correlation with spectroscopic and imaging data, and sophisticated modeling. The work was painstaking, but it was through these details that the character of 3I Atlas emerged. Not as a simple icy rock, but as a dynamic world responding to the sun's heat in intricate ways. Orbital evolution and long-term trajectory. While much attention focused on the short-term non-gravitational acceleration, understanding the long-term orbital evolution of 3I Atlas required looking both backward and forward in time. Where did this object come from, and where is it going? Answering these questions involved integrating the orbit through the gravitational field of the galaxy, accounting for encounters with stars and molecular clouds, and considering the cumulative effects of the anomalous acceleration. Tracing the orbit backward in time, astronomers calculated that 3I Atlas entered the solar system from the direction of the constellation Lyra, moving at a velocity of about 23 kilometers per second relative to the Sun. This velocity, called the hyperbolic excess velocity, is what the object had at infinite distance from the Sun, unaffected by solar gravity. It represents the object's motion through the local interstellar medium. The velocity is typical for stars and interstellar gas in the solar neighborhood, confirming that 3I Atlas is a genuine interstellar visitor and not a solar system object on an extremely long period orbit. Extending the trajectory further back, before the object enters the Sun's gravitational influence, the orbit becomes a straight line through space. Following this line backward for thousands or millions of years, researchers searched for potential origin points. Did 3I Atlas come from a nearby star system, ejected during planet formation or a later dynamical event? Or has it been wandering the galaxy for billions of years, passing through the interstellar void without a clear home? Nearby star catalogues were searched for stars along or near the inferred trajectory. A handful of candidates were identified, stars that 3I Atlas might have passed close to within the last few million years. But the uncertainties in both the object's trajectory and the star's motions were large enough that definitive identification was impossible. Additionally, interstellar space is vast, and the probability of passing close to any particular star is low. Most likely, 3I Atlas originated from a star system far away, possibly hundreds of light years distant, and has been in interstellar transit for tens of millions of years or more. During such a long journey, the object would have been exposed to cosmic rays, ultraviolet light from distant stars, and the occasional passage through molecular clouds. These environmental factors can alter surface chemistry, eroding ices, creating organic compounds through radiolysis, and gradually darkening the surface. The properties observed today are the cumulative result of both the object's formation environment and its subsequent history. Disentangling these influences is challenging but important for understanding not just 3I Atlas, but the population of interstellar objects generally. Looking forward, the trajectory after leaving the solar system is equally uncertain due to the non-gravitational acceleration. If the acceleration continues as the object moves away from the Sun, it will gain additional speed beyond what gravity alone provides. This extra velocity changes the ultimate trajectory through the galaxy. Depending on the magnitude and direction of the continued acceleration, 3I Atlas could end up on a significantly different path than predicted by gravitational dynamics alone. Orbital integrations that include the measured non-gravitational acceleration show that the object's velocity could increase by several kilometers per second over the next few years as it travels outward. This might seem small, but over galactic timescales, such velocity changes accumulate. The difference could determine whether 3I Atlas eventually falls back toward the galactic plane or continues outward into the galactic halo, whether it passes near other star systems or wanders through empty space, and ultimately whether it ever encounters another planetary system or remains a lone wanderer. One intriguing aspect is the possibility that non-gravitational forces are common among interstellar objects. If so, their trajectories through the galaxy are not purely ballistic, but influenced by ongoing processes like outgassing driven by cosmic ray heating or other exotic mechanisms. This would mean that the distribution and velocities of interstellar objects differ from simple gravitational predictions, with implications for how we model the interstellar population and how we predict encounter rates with our solar system. Galactic tides also play a role over long timescales. As objects orbit the galaxy, they experience gravitational forces from the overall mass distribution, including the galactic disk, bulge, and dark matter halo. These tides can alter orbits gradually, changing eccentricities and inclinations over millions of years. For 3I Atlas, its current velocity and trajectory suggest an orbit that takes it far from the galactic plane, possibly into the halo, before returning. The orbital period around the galaxy could be hundreds of millions of years, meaning 3I Atlas has completed only a few dozen orbits since the galaxy formed. Encounters with giant molecular clouds are another consideration. These clouds, dense regions of gas and dust where stars form, are scattered throughout the galaxy. Passing through a cloud subjects an object to drag from the gas, potentially slowing it down or altering its trajectory. For small objects like 3I Atlas, the effect is tiny but non-zero. Over billions of years, multiple cloud passages could cumulatively affect the orbit. However, the galaxy's molecular cloud distribution is not well enough known to predict specific encounters for any individual object. The long-term fate of 3I Atlas is therefore uncertain. It will leave the solar system and return to interstellar space. But where it goes from there depends on factors we can't fully predict. It might pass near another star in 1 million years, or it might drift for billions of years without any close encounters. It might remain bound to the galaxy's gravitational potential, or if the non-gravitational acceleration is strong enough and sustained long enough, it might eventually reach escape velocity and leave the galaxy entirely, becoming an intergalactic wanderer. These long-term questions connect the study of 3I Atlas to broader astrophysical contexts. Understanding interstellar object dynamics informs models of planet formation and ejection, the structure and evolution of the galaxy, and even the potential for panspermia, the transfer of life, or its precursors, between star systems via such objects. Each interstellar visitor we study adds a data point, and as the sample grows, patterns will emerge that illuminate the nature and history of these cosmic travelers. Comparative planetology beyond the solar system. 3I Atlas offers a unique opportunity to practice comparative planetology on an object formed in another stellar system. Everything we've learned about planets, moons, asteroids, and comets has come from studying our own solar system, with limited glimpses of exoplanets through indirect methods. Interstellar visitors, like 3I Atlas, bridge this gap bringing samples from other systems directly to us for detailed study. What does 3I, Atlas, tell us about planetary system formation elsewhere, and how does it compare to what we know from our own cosmic backyard? Planet formation theory is built on observations of the solar system combined with models of disk dynamics and chemistry. The prevailing picture is that planets form in protoplanetary disks, flattened clouds of gas and dust orbiting young stars. Dust grains stick together, growing into pebbles, then planetesimals, and eventually planets. Icy bodies like comets form in the outer regions, where temperatures are low enough for water and other volatiles to condense. Some of these bodies are incorporated into planets, while others are ejected into interstellar space through gravitational interactions. The composition of 3I, Atlas, provides clues about the disk from which it formed. Spectroscopic observations showing water, organics, and trace gases suggest formation in a cold environment where these materials could condense. The ratios of different molecular species, like the carbon monoxide to water ratio or the presence of specific organics, reflect the temperature and chemical conditions in the natal disk. Comparing these to solar system comets reveals both similarities and differences. Solar system comets show a range of compositions, but there are family resemblances. Jupiter family comets, which have orbits controlled by Jupiter's gravity, tend to have certain compositional characteristics, while Oort cloud comets, coming from the distant reservoir surrounding the solar system, have others. The differences likely reflect formation at different distances from the Sun and different thermal histories. 3I, Atlas's composition, doesn't fit neatly into either category. Some ratios match solar system comets, others don't, suggesting formation in a disk with a different temperature profile or chemical inventory than the solar nebula. Isotopic ratios are particularly valuable for comparative studies. The ratios of hydrogen to deuterium, or different isotopes of carbon, nitrogen, and oxygen, are set by nuclear processes in stars and by chemical reactions in cold interstellar clouds and protoplanetary disks. These ratios vary between different reservoirs in the galaxy. Measuring isotopic ratios in 3I, Atlas material, would allow direct comparison to solar system values and could indicate whether the object formed from materials similar to or different from what made the Sun and planets. Unfortunately, measuring isotopic ratios remotely is extraordinarily difficult. It requires high-resolution spectroscopy to resolve the small wavelength shifts between spectral lines from different isotopes. For 3I Atlas, some attempts were made to measure deuterium to hydrogen ratios in water using space-based ultraviolet spectrographs, but the signal-to-noise was insufficient for a definitive measurement. Future missions carrying sample return or in-situ analysis capabilities would be needed to nail down isotopic compositions precisely. The size and structure of 3I Atlas also inform formation models. If the nucleus is a single consolidated body, it likely grew through gentle collisions in a quiescent disk environment. If it's a rubble pile of smaller fragments loosely bound by gravity, it might have formed through more violent processes or experienced collisions that shattered a larger parent body. The density inferred from mass and volume estimates provides constraints. Low densities, around a few hundred kilograms per cubic meter, suggest high porosity, consistent with a rubble pile structure. Higher densities would indicate a more consolidated body. For 3I Atlas, density estimates are highly uncertain because mass is poorly constrained. Without knowing the mass precisely, the density could be anywhere in a wide range. Observations of the object's response to solar heating and outgassing provide indirect constraints. A low-density, highly porous object would have different thermal and mechanical properties than a solid one, affecting how it outgasses and how it responds to internal pressures from sublimating ice. The observed behavior is consistent with moderate porosity, similar to solar system comets, but doesn't rule out more extreme values. The dynamics of ejection from its home system also matter. For 3I Atlas to be travelling through interstellar space, it must have been ejected with sufficient velocity to escape its parent star's gravity. This typically happens through gravitational scattering by planets. In our solar system, Neptune and Uranus are thought to have ejected large numbers of icy bodies into the Oort cloud and beyond during the early solar system's dynamical upheaval. Systems with giant planets in different configurations would eject bodies with different velocity distributions and at different rates. Population synthesis models predict that the number of interstellar objects passing through the solar system should reflect the average properties and ejection efficiencies of planetary systems across the galaxy. The more systems there are with giant planets, and the more violent their dynamical histories, the more interstellar objects we should detect. The discovery rate of interstellar visitors thus provides a statistical measure of planet formation and evolution across the galaxy. With only 3 detected so far, statistics are poor, but as numbers grow, patterns will emerge. Comparing 3I, Atlas to Oumuamua and Borisov highlights diversity. Oumuamua appeared asteroidal, with no detected activity and an unusual shape. Borisov was clearly cometary, with a composition similar to solar system comets. 3I. Atlas is cometary but with anomalies. This diversity suggests that other stellar systems produce a range of small body types, just as ours does. Some systems might produce more asteroids than comets, or vice versa, depending on their formation history. The relative numbers of different types of interstellar objects inform us about these differences. Ultimately, studying interstellar visitors like 3I, Atlas, is a form of astronomy and planetary science rolled into one. We're observing objects from other star systems, learning about their compositions and behaviors, and using that information to test and refine our theories of how planets and small bodies form. Each visitor is a sample from a distant planetary system, a messenger carrying information across light years. The trajectory anomaly, while a puzzle for orbital mechanics, is also a clue about the object's physical properties, which in turn reflect its formation and history. Solving the puzzle is not just about explaining the motion, but about understanding the object in its full context as a product of another world. The search for precursor objects. If 3I, Atlas, is unusual, are there other objects like it, either in interstellar space or lurking undetected in our own solar system? The search for precursor objects, bodies that might share 3I, Atlas's characteristics or exhibit similar anomalies, has become a focused effort. Identifying such objects would help determine whether 3I, Atlas, is a one-off oddity or representative of a broader population with common properties. In the solar system, long-period comets and objects from the Oort cloud are the closest analogues. These bodies spend most of their time far from the Sun, in cold storage where they preserve their primordial compositions. When their orbits bring them into the inner solar system, they become active and observable. Some long-period comets have shown unusual behaviors that, in hindsight, resemble aspects of 3I, Atlas. Strong non-gravitational accelerations, unexpectedly high activity levels, or spectroscopic oddities have been noted in a handful of cases. Researchers combed through decades of cometary observation archives, looking for objects with similar signatures. A few candidates emerged, comets whose orbits showed non-gravitational terms larger than easily explained by their observed activity. In some cases, the discrepancies were attributed to measurement errors or incomplete data. In others, the anomalies persisted but were never fully explained. These archival cases are being re-examined with modern techniques and data, searching for patterns or clues that might have been missed. One intriguing possibility is that some long-period comets are actually interstellar objects that were captured into bound orbits around the Sun. Gravitational interactions with planets can, in rare cases, slow an incoming interstellar object enough that it becomes bound. Once captured, the object would appear in all respects like a long-period comet, making it difficult to distinguish from native solar system bodies. Detailed orbital analysis can sometimes reveal capture signatures, like an unusually high inclination or a trajectory that doesn't fit the expected distribution of Oort cloud orbits. For 3I, Atlas, the orbit is clearly hyperbolic, leaving no doubt about its interstellar origin. But if there are captured interstellar objects among the known comet population, studying them could provide additional examples of bodies formed in other stellar systems. Some researchers have proposed that a significant fraction of long-period comets might be captured interstellar objects, though this remains controversial. Confirming such a hypothesis requires statistical analysis of orbital distributions and, ideally, compositional measurements that show clear differences from solar system norms. Another search target is inactive or dormant objects in the outer solar system. Not all icy bodies become active comets. If an object's surface is covered by a thick, non-volatile crust, or if it has exhausted its near-surface volatiles, it can remain dark and inactive even when close to the Sun. Such objects are difficult to detect because they don't have bright comet to make them stand out. They appear as faint, star-like points, indistinguishable from distant asteroids or faint stars, except through repeated observations that reveal their motion. Surveys designed to find near-Earth asteroids and other solar system objects occasionally pick up these dark, distant bodies. Some turn out to be extinct comet nuclei, revealing their nature through spectroscopic signatures, or by suddenly becoming active when a change in their orbit brings them closer to the Sun. Could some of these be interstellar objects that passed through the solar system long ago and were captured? Or could they be solar system objects with unusual compositions that make them similar to 3I, Atlas? The challenge is identification. With limited data, distinguishing between an unusual solar system object and a captured interstellar one is difficult. Composition is key, but getting detailed compositional data on faint, distant objects requires significant telescope time. Prioritizing targets for follow-up requires educated guesses about which objects are most likely to be interesting, often based on preliminary observations that hint at something unusual. Advanced survey telescopes coming online are changing the game. The Vera Rubin Observatory, with its ability to repeatedly scan the entire visible sky every few nights, will discover thousands of new faint-moving objects every year. Among these will be more interstellar visitors passing through, but also potentially captured objects and solar system bodies with unusual properties. The sheer volume of data will require automated classification and machine learning to identify candidates worthy of detailed follow-up. Interstellar space itself is the ultimate reservoir. 3I, Atlas, came from there, and countless others are out there, drifting between the stars. We only see them when they pass close enough to the Sun to be detected. The number of interstellar objects passing through the solar system at any given time is estimated to be on the order of 1 to 10, depending on assumptions about their size, distribution, and number density in the galaxy. Most are too small or too far from Earth to detect with current telescopes. The discovery rate of interstellar objects is expected to increase dramatically with better surveys. As telescopes become more sensitive and cover more sky more frequently, the detection rate will rise. Within a decade, we might go from having detected 3 or 4 interstellar objects to dozens or even hundreds. This growing sample will reveal the diversity of the interstellar population, including whether objects like 3I, Atlas, with their trajectory anomalies and other oddities, are common or rare. Finding precursor objects, whether in archived data, in the outer solar system, or in future surveys, is essential for context. If 3I, Atlas, is unique, its anomalies might be due to specific, rare circumstances. If similar objects are found, patterns will emerge, pointing toward common physical mechanisms. The search is ongoing, a combination of data mining, targeted observations, and patient waiting for the next discovery. Each new find adds a piece to the puzzle, bringing us closer to understanding not just 3I Atlas, but the broader population of which it is a member.